Welcome to this lesson on diverging lenses, where we explore how these fascinating optical devices spread light apart. Diverging lenses are an essential part of optics and have numerous practical applications in our daily lives. Let's begin our journey into understanding how these lenses work and why they're so important. A diverging lens is a special type of lens that has a unique shape. It is thinner at the center and thicker at the edges. This shape is exactly opposite to what you might find in a magnifying glass. Because of this distinctive shape, diverging lenses are also called concave lenses or negative lenses. The key behavior of these lenses is that they cause light rays to spread apart or diverge when light passes through them. This diverging property is what gives the lens its name. Diverging lenses come in several different shapes, but they all share the common feature of being thinner in the middle. The most common type is the biconcave lens, where both sides curve inward. There's also the plano-concave lens, which has one flat side and one curved side. Finally, there's the concavo-convex lens, where both sides are curved but at different amounts. Regardless of the specific shape, all diverging lenses have thicker edges and a thinner center, which is the key to their light-spreading behavior. Let's examine what happens when light rays pass through a diverging lens. When parallel rays of light approach the lens from one side, they enter the lens and are refracted, which means they bend as they pass through the glass. After exiting the lens, these rays spread out and diverge away from each other. The rays appear to be coming from a single point behind the lens, even though they never actually pass through that point. This spreading behavior is the fundamental characteristic of diverging lenses and is what makes them useful for many applications. Every diverging lens has two important features: the focal point and the focal length. The focal point, represented by the letter F, is a virtual point from which the diverging light rays appear to originate. If you trace the diverging rays backward, they all seem to meet at this focal point. The focal length, represented by the letter F, is the distance from the center of the lens to the focal point. For diverging lenses, the focal length is always negative, which is why they're sometimes called negative lenses. The focal point is located on the same side as the incoming light, unlike converging lenses where it's on the opposite side. Diverging lenses have a remarkable property. They always form the same type of image, no matter where you place the object. The image formed is always virtual, meaning it cannot be projected onto a screen. It is always upright, which means it has the same orientation as the object. The image is always diminished, or smaller than the actual object. And finally, the image is always located on the same side of the lens as the object, between the lens and the focal point. What makes this truly special is that these properties never change, regardless of how far or how close the object is to the lens. The behavior of diverging lenses can be described mathematically using the lens formula. This formula states that 1 divided by the focal length equals 1 divided by the image distance minus 1 divided by the object distance. In this equation, F represents the focal length, V represents the image distance from the lens, and U represents the object distance from the lens. For diverging lenses, there's an important convention to remember. All three distances are considered negative. The focal length is negative because it's a diverging lens, the image distance is negative because the image is virtual, and the object distance is negative according to the sign convention used in optics. Diverging lenses have many practical applications in the real world. They are most commonly used in eyeglasses to correct myopia or nearsightedness. In this condition, light focuses in front of the retina, and diverging lenses help spread the light so it focuses correctly on the retina. Diverging lenses are also used in telescopes as eyepieces to increase the field of view, allowing us to see more of the sky at once. In camera lenses, they are combined with converging lenses to control zoom and focus. You can even find diverging lenses in door peepholes, where they provide a wide-angle view of the area outside, helping you see who's at your door. These applications demonstrate how important diverging lenses are in both correcting vision and enhancing our ability to observe the world around us.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.